This is the solution for in-class problem 6. This is problem 134 from the textbook. So you see here we have this pipe and a rod, um, and we have the dimensions of the pipe, so the inner and outer dimensions, and then the diameter of the rod, which is a solid rod. We're supposed to find the average normal stress at points D and E. So that's D, average normal stress of E, and represent the stress on a volume element at each of these points. So we'll start with D, and I'm just going to slice it through there. So draw a free body diagram. So this is D, A. We have a 60 kilonewton force at the end. And I guess we have the dimensions of it. Actually, they don't give us the dimensions of it. I don't think it ends up mattering. And then the other thing that we have is the normal force at D. And so we're interested in the stress at D. So the stress at D equals the normal force at D over the area, the cross-sectional area. So we need the normal force. So if we look at our free body diagram, we sum the forces in the x direction equals 0. We get that 60 kilonewtons minus ND equals 0. So ND equals 60 kilonewtons. That's in compression. And then we need the area. And this one is a pipe. And so we need to the area of the pipe. So we have a circle, our two circles. We know the inner diameter is 25 millimeters. And then the outer diameter is 30 millimeters. So that area is going to be the area of the outer circle. So pi times r. So the radius would be half of 30, which is the diameter. So 15 millimeters. Pi r squared minus the area of the internal circle, which is pi times the radius of the diameter is 25, so it'd be 12.5 millimeters squared. I'll use my calculator to figure that out. And I get 215.98 millimeters squared. So see, I'm keeping 5 significant figures now. I'm actually saving it in my calculator to make it even more accurate at the end. So now we have the area and we have the normal force, so now we can solve the equation. So the stress D equals 60,000 newtons divided by 215.98 millimeters squared. And we know newtons over millimeters squared are megapascals. And so with that, we get 277.8 megapascals. And that would be in compression. And then they also asked us to represent the stress on a volume. So I'm going to draw my little cube here. And we have 277.8 megapascals. And on the other side. Okay, so that's the first part. And then we also want to do the same for part E. So I'm going to draw a free body diagram like we did before from E to C, so that end of it. And this part is a rod. So we have 20 kilonewtons. We have the normal force at E. And then we're going to solve this. The stress at E is going to equal the normal force at E over the area. So we need that normal force. So we sum the forces in the x direction equals 0. So equal negative NE plus 20 kilonewtons. So NE equals 20 kilonewtons. We really could have figured that out by just by looking at the free body diagram. And then the area, the rod is 15 millimeters. In diameter. So the area is going to equal the radius, or pi r squared. So pi times the radius, which would be 15 millimeters, is the diameter divided by 2 squared. So that area equals 176.7 millimeters squared. So now we can find that stress because we have all the components. So stress of E equals the normal force at E, which is at 20 kilonewtons, divided by, actually, because we know newtons divided by meters squared is megapascals, so 20,000 newtons. So I was just changing that 20 kilonewtons to 20,000, divided by 176.7 millimeters squared. And that's going to give us 113.2 megapascals. That's in tension. Put a box around my answer, and then I'm going to draw my volume element. As the stress of E is 113.2 megapascals. And that's it.